So we're going to spend a little bit of time figuring out how to count things. We need to know how to count how many equally likely outcomes there are sometimes. And so we'll have to look at some strategies for counting. Like you might want to count how many ways you can make a straight flush or a full house in card games. Or you might want to decide how many ways you could do things like that, and where you know there's some equally likely outcomes underlying the experiment. And so finding probabilities involves counting how many of them belong to a particular kind of outcome. So learning how to count is necessary if you're in that kind of situation, which we'll be in just for a short period of time. So it's section 5.5. It's called Counting Techniques. It has a fancier name in mathematics. It's called combinatorics. It has to deal with counting. You can actually get whole math degrees in combinatorics, and still we're only going to do just one day, so figure if it could take 3 or 4 years to learn everything about counting and we're just spending 1 hour on it, we won't get very deep into counting. But even so, it's easy to ask questions that are hard to answer in counting. And so even easy questions we might not be able to answer, the ones that look easy. Of course, easy questions you can answer, but they might look easy and turn out to be hard. So here we go. We're just going to look at some counting techniques, and then we'll count some stuff up, and then we'll move on. So the basic idea, at least to begin with, for counting, is this thing called the multiplication rule. It says, if an operation involves k steps, and step I has n sub I possibilities, we have to use subscripts here, I'll see a way around it, then the operation can be performed in the product of the number of ways you are allowed to use at each step. So there's n1 ways for the first step, n2 ways for the second step, and so on. So you count the number of ways for each step, and you multiply them together, and that's the number of ways the operation can be performed. So here's an example. You've got license plates that have letter, 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 number, number, number. And you want to count how many license plates you can make. So, well, first you have to, we'll think of the steps like this way. Pick a first letter, step 1. Pick a second letter, step 2. Pick a third letter, step 3. Then number, step 4. Number, step 5. Number, step 6. And then we count the number of ways you can do that. So there's 26 letters you could choose. 26 letters you could choose. 26 letters you could choose. And then digits, 0 through 9. There's 10 ways. Like that. 10 ways, 10 ways. Okay. So sometimes these numbers become pretty big. I did this in advance. 175. No, I don't believe that. What I've written on my sheet. Let's see what it actually is. Because I've got a comma in the wrong place. Let's see. So it's 26 times 26 times 26 times 1,000. So the number is 17 million. I just said my comma in the wrong place. 17,576,000, like that. Exactly. So in a state that has more than 17 million drivers, that wouldn't be enough license plates for everyone to have a different license plate. So you know a lot of states, they've used up the 6-digit version. Letter, 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 number, number, number. Then they go number, 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 letter, 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 and then eventually they have to do 7 digits after they've used up every reasonable combination of letters and numbers. Because they burn through license plates, and they don't want to repeat them. So you've got cars that aren't being driven, or you have license plates that are on a car that's in the junkyard. You know, in Colorado, you get to keep your license plates, so you probably maybe don't need as many different license plates. You might be able to even keep them in the family if you wanted to, I'm not sure. So another example is number of bank card codes, bank card codes, 4 digits, blah, 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 blah. And in my bank, I think they allow repeats, but I think in some banks they don't. So how many ways can you make a 4-digit number with no repeats? So the steps are pick a first number, pick a second number, pick a third number, pick a fourth number. So you can pick a first number in 10 ways. It's 0 through 9. Then I used up a number, I can't have repeats. So I've got 9 numbers left for the second number, and like this. And that pattern continues. 10987. So that's 5040. Like that. And then I get hungry around this time of the day. Pick 3 desserts from 20. So a dessert tray comes by your table, and they're not going to come back for a while. It says you can pick any 3 desserts you want, but you can't pick 2 that are the same. So that's something like having bank card codes. So you have 20 choices for your first try off the tray, and then 19, and then 18 like that, multiplied together. So that's 6840. So when you're not allowed to repeat, or you use up possibilities and the numbers decrease, you end up multiplying things like number, number less, number less, number less, like that. And those kinds of patterns are basically most easily symbolically written using factorials. So we'll use some factorials to do our work. There's some definitions. 0 factorial is defined to be 1. The reason for that we will not talk about because we never do 0 factorial. 1 factorial is 1, so it's basically factorials are the number and all the numbers less down to 1 multiplied together. So then 1 is 1 and all the numbers less, which there aren't any, multiplied together. Does that make sense? And for other numbers, you take that number bigger than 1. I should put that n bigger than 1 so that we haven't said anything about a negative number factorial, which I don't want to talk about. So like 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 till you're done. And that's 720. And then 25 factorial is a very big number. What you do if you want it, though, well, you can actually put all those numbers in your calculator. But if you want a quick way to get factorials, you go to your calculator, you go to Math, and you go over to Prob, PRB, because factorials happen in probability. So there's a bunch of probability stuff here in Math Prob. And then you scroll down to factorial. So Math Prob Factorial. And then you need to have typed the number first. Okay, so I get out of here and I put 25 in. So I go 25, and then I go Math, and I scroll over to Prob, and I scroll down to Factorial, which is number 4. I hit Enter. And that gives me 25 factorial on the screen, and then I hit Enter again. And I get 155.112.1004 E25. Oh, I copied off my notes wrong. Okay, that's good. So this E25 means times 10 to the 25th. So calculators have a different way of expressing scientific notation. When the numbers get big, most of them resort to scientific notation because you can't put the full number on the screen. So the decimal point is somewhere, but it's probably way over to the right, past the digits you have. So they resort to scientific notation, where this is a number from 0 to 10, or scientific notation. This number is 1 through 9 in front here, and then decimal point and stuff, and 10 to the something, right? So 0.55 would have been 5.5 times 10 to the 24th, I suppose. And there we go. Okay, so that's, beware when you see E or some other crazy letter here and then a number next to it, next to something in a calculator output. It's probably scientific notation. So that represents the exponent on 10. So we said a minute ago that factorials show up, at least things that look something like factorials here. You're multiplying numbers less, less, and less, but you're not going all the way down to 1. So we have to find a way to make that happen. We'll do that shortly, but the factorial by itself finds its way into counting in this way. The number of ways to place k different items in order is k factorial. And so that's called a permutation. Of k items. So we can get different ways of thinking about permutations of items this way. Let's see how many 4-letter words you can make using A, B, C, D, each one only once, and in every order possible. So the answer should be 4-letter word, 4 factorial, which is 4 times 3 times 2 times 1. You kind of see why that would be. I'm trying to make a word, I have to pick a first letter. There's 4 choices. I've used up a letter, then I have to pick a second letter. Then there'd be 3 choices, and then I'd use up 2 letters. And then I'd have to pick one of those 2 letters for the third letter, and then there'd be only 1 left for the 4th letter. So number of choices times number of choices times number of choices times number of choices is the multiplication rule. And out comes 24. 10-digit codes, 0 through 9, no repeats. 10 factorial. 10 choices for the first digit, and 9 for the second, and so on. So I'm going to type 10 here. I'm going math. No, I'm not. I'm typing 10 here. Going math, prob, down to factorial. There it is. Hit enter. 362880. 362880. Correct. 10 factorial. 362880. So that's the beginning of counting. We now know how to count things like bank card codes and permutations of letters, and we'll just try to make that a little more sophisticated shortly. We will just scratch the surface of that type of thing. You could find out like how many, well, we'll see that. If you're playing the lottery by picking some numbers out of a batch of numbers, how many ways can you do that? Stuff like that. And we'll be doing that in a minute. Here we go.